All right, y'all. So let's pick up where we left off last time. We started talking about these experiments we call titrations, where we have a solution in a flask, and then we're adding in another solution using our burette, our titrant. All right. And we set our goal, because you've seen titrations before, but our goal in this course here is going to be to calculate the pH at every point along the way of that titration. Meaning I add in no base, what's my pH? I add in 5 drops of base, what's my pH? I add in 10 drops, et cetera, et cetera. We should be able to calculate the pH at any volume of base added. And what we said was we carved up this pH curve right here into these 4 regions. And we had a slightly different strategy for solving pH depending on those regions. All right? Our first region being before our titration has happened at all. All right? All we have is a flask of acid. And then we get to this region where we've started adding acid, started adding base, but we haven't quite yet reached our equivalence point. Our equivalence point is when the amount of acid is equal to the amount of base in that flask, right? And that's true in terms of concentration, but also in terms of millimoles. And this was important because throughout our pH curve here, we always had to calculate how much of this acid-base reaction has occurred. And since in a titration we're always changing volume, we had to use our ice table in units of millimoles. All right, so in this second region here, just to remind you, what we did is we said, all right, here's my acid-base reaction. We learned how to predict products of acid-base reactions, right? Your acid is going to decrease in number of protons and decrease in charge. Your base is going to increase in number of protons and increase in charge, right? These conjugate pairs. So we know how to predict the products of these reactions. And then we use this ice table here to keep track of how much reaction has occurred. Importantly, we were given a volume and a concentration. And so when we were doing our initial amount here, we were calculating in terms of millimoles, where we were taking milliliters, multiplying it by moles per liter. The liter part cancels out, but we're left with the milli and the moles. Right? So that's our units for our ice table when we're keeping track of our reaction in our acid base, in our titrations here. Okay? So where we left off last time was talking about weak acid, strong base titrations. And we did this first region here, this very first data point, which is just calculating the pH of a solution of weak acid. And we learned how to do that previously. So we did our acid dissociation reaction, our Ka expression, our ice table to fill in our Ka expression, plugged it in and solved. All right, so now we're going to move to region 2 here. This is before we get to that equivalence point. We also have that equivalence point, so I guess we could just put that down here. All right, and our equivalence point means the exact same thing. This is when my millimoles of acid, equals millimoles of acid, we can say initial, equals millimoles of base added. All right, that's again going to be our third region, but we're not quite there yet. We're in this portion of our curve here. So we still have an excess of that weak acid, but now we've started to add base in there. All right, so we're going to take that same solution, 70 mils of 1.25 molar acetic acid. We looked up our Ka value for that acid, but now we're going to add in 45 mils of 1.13 molar sodium hydroxide, and we want to know what the pH of our solution is. Okay, so I'm going to give you, based on what we've discussed up until this point about acid-base reactions, about how we combine acids and bases, I want you to see how much of this you could do on your own. We need this acid-base reaction. All right, and then we need an ice table to keep track of how much reaction has occurred. And again, we're going to need to do this in units of millimoles. All right, so I'm going to give you a few minutes here to set that up. I'm going to give you a head start, and then I'll kind of quietly fill in on my own up here. was testing you. Unit's got to be millimole. All right, so my acid-base reaction here is that acetic acid reacting with my sodium hydroxide, but specifically the hydroxide. Remember, so what we talked about is when you see that sodium, you want to say, I know that's just playing the role of the counter ion, so I'm going to get rid of it and replace it with the minus sign. Here's what's actually playing the role of the base in my chemical reaction. If you really wanted to include it, you could. You would just have to include it as the counter ion to both negatively charged ions on both sides of your reaction, right? If it appears on one side, it's got to appear on both sides. So you can include it. But what I said is I would love for you to get in the habit of recognizing it as being a counter ion and not actually participating in this chemical reaction at all. And then I'm going to do my ice table in millimoles. I will say, I've included it up until this point, but always made the point that you can ignore how much water is being produced in this reaction. And that's going to be the same for every one of these reactions that we're talking about, since what we're talking about pH and water is neutral. If you just left this column off of here altogether, you'd be perfectly fine, right? We can keep track of how much water is produced in the reaction, that's fine, but we don't have to. All right, and then in order to get to millimoles here, I'm going to take my milliliters, multiply it by that molarity moles per liter. All right, so I get 87.5. And again, my units work out here where the liters cancel out, and I'm left with millimole. All right, same thing over here. My 50.85 millimoles, and I don't have any of my products produced before this reaction has occurred. My change box, that variable X, my reactants are going to decrease in concentration My products increase in concentration. All right, so we're left with 87.5 minus X, 50.85 minus X, X, and X. All right. So how are we going to solve for our value of X here? Well, importantly, this reaction is not a reaction that I think about as being in this dynamic equilibrium. This is not an equilibrium problem. How do I know it's not an equilibrium problem? How do I know I'm not going to be using a Ka? Well, the arrow definitely gives it away, but I put that arrow there. So you're going to have to write that equation, right? So how would you know if I just gave you this problem? The hydroxide, which is the strong, right? So anything strong means that reaction always goes 100% to completion here. Our strong always reacts. All right, so that means that if this reaction goes to completion, then whatever my limiting reactant is, which I can tell by comparing how much of reactant A and reactant B I have, right? How much of this weak acid versus this strong base I have. I know that all of that limiting reactant is going to be consumed, meaning my value for X must be that 50.85. All right, so this is what we called our ICIS table, where you have this little solve box at the bottom here. We solve for that value of X and then plug it in across the board here. All right, 36.65 millimoles of that acetic acid, 50.85 millimoles of its conjugate base, and we made 50.85 millimoles of water. All right. So let's remember what we did back when we were looking at region 2 of our strong acid, strong base reaction. What we did is we got to the end and said, all right, this is the solution that I'm left with at equilibrium. So what remains in that solution at equilibrium? And we said, well, there's none of that strong base. And then we didn't care about the chloride or the water produced because those were both neutral. So we're going to look at this solution now that it's come to equilibrium in region 2. And we're going to figure out what we have here. All right, again, we don't have any of that strong base rather. All right, what else don't we care about up here? The water. We don't care about the water because it's neutral. All right, but what about my other product? Am I allowed to ignore how much of my conjugate base was produced in this particular example? No, why not? Remember, the conjugate of something strong is itself always neutral. But this is a weak acid, which means that its conjugate is also a weak base. Right? Weak and weak are conjugates, just like strong and neutral are conjugates. So what I have is a solution of weak base over here, or rather my product's a weak base, so no, I can't ignore that. That is going to contribute to the pH of my solution. So what I have now that we've reached equilibrium is a solution of weak acid and its conjugate base. How do I figure out the pH of a solution of weak acid and its conjugate base? Yeah, because a solution of weak acid and its conjugate base is a buffer solution, right? So region 2 of a weak acid strong base titration, we call this the buffer region. Because we've added some base in there, but we've had an excess of that weak acid, meaning that we've made some weak base, so now we got a mixture of both. All right? So in order to calculate our pH of this solution, we get to use that equation we can only use for buffers, our Henderson-Hasselbalch equation. All right, so Henderson-Hasselbalch is pH equals pKa plus the log of base over acid. Okay? But now we can make our lives a little bit easier. You know, in all these other problems, when we got to this step here, we were like, oh crap, we need a concentration. And our table was in millimoles. So now we got to go back to concentration. All right? So I'm going to do this the long way real quick just to prove a point. pH equals pKa plus the log. All right, if I was going to do my base, which one's my base? Acetic acid or acetate? The one on the left or the one on the right? All right, this is my conjugate base here. So that would be my 50 millimole, or 50 point whatever, what was it, 85 millimoles divided by, what would my volume be of this solution? Tough mental math. 70 plus 45 here takes us to 115. All right, 115 milliliters. And we can just convince ourselves real quick that the milli indeed cancels out, leaving us with moles over liters or molarity. All right, but then I'm going to take this and divide it by my acid concentration, which is that 36.65 millimoles. But what's the volume of this weak acid solution now? Also 115. All right, and notice that we got 115 in the numerator, 115 in the denominator. So since we're taking a ratio here, it turns out that we can also simplify our Henderson-Hasselbalch equation to being pH equals pKa plus the log of millimoles base over millimoles acid. Saves us a conversion step. All right, so given this particular solution here, as well as the fact that we noted the Ka of acetic acid was 1.8 times 10 to the negative 5, and of course we got this value from that table, that constants page. All right, everybody take a second and calculate the pH for me. What's up?
On the chem, do you want, when we're doing not the pKa, but the long part of the base for acid, do you want us to write like 3.85 millimole over 150 milliliters? Like, do we have to show that?
No. So basically what I was trying to prove here is you don't have to convert it to volume because it's the same in the numerator and the denominator. We're taking a ratio of those concentrations, so the volume actually cancels out, so it's the same. So you can just keep it in millimoles. And I guess to be clear, that's true always of all, this point in our titration. It's not like a special case here. All right, so we got a pH here of 4.887. Again, because we used our ice table, we're just going to kind of arbitrarily say 3 decimal places. It's always a good idea to go back and do a little bit of a sanity check here. All right, we had established that in region 1, the very first point in our titration curve here, we said was at a pH of 2.324. Makes sense, it's an acidic solution. All right, we've started adding our strong base in there, but we still have an excess of that weak acid, weak base combination, so our pH is still in that acidic region, but now just barely, right? Because we don't have a strong acid solution where it should be super low. We have a weak acid solution, so it should be closer to that neutral level there. All right, so this part here on our titration curve, again, we were breaking it up into these regions. This region here is what we call the buffer region. Since we've started our titration, we still have to do what we've always started with here. We have to calculate the amount of reaction that has occurred and again, since we are doing a titration where we're changing our volume, we had to do so in millimoles. But when it got to the point where we were calculating our pH, we got to use that calculate pH for a buffer. And again, for buffers, we get to use that special equation, that Henderson-Hasselbalch equation. All right, so region 3 here, that's now that equivalence point where our millimoles of acid initial equal the total amount of base added. All right, so how are we going to go about dealing with this region? Region 3, our equivalence point. Okay, we're gonna stay with that same solution, our solution of 70 milliliters of 1.25 molar acetic acid. All right, but now I want to know what volume of NaOH, specifically that 1.13 molar NaOH, was added to reach our equivalence point. All right, so how are we supposed to do this? Well, we got to remember what it means to be at the equivalence point, which means that the millimoles of acid that we had initially are going to equal the millimoles of base that we added. And we're going to be good and say strong base here. I'll show you why in a second. right, so how many millimoles of acid did we add? Or did we have initially, rather? According to our ice table, we had that 87.5 millimoles of our weak acid initially. Which means how many millimoles of strong base have been added? 87.5 millimoles of NaOH. All right, so I know how many moles I need, and I have my concentration, which lets me jump from units of moles to liters, or liters to moles. So we're going to take our 87.5 millimoles of our NaOH, and we're going to divide it by that 1.13 moles of NaOH in 1 liter. And it looks like these units don't cancel out, and they don't cancel out completely, but importantly, the moles do cancel out, and so what I'm left with is a volume in milliliters here. All right, the same little trick we were using with our millimoles, we can use with our volume as well. So this takes me to 77.433 milliliters. Okay, so we're doing the same chemical reaction here, so I'm just going to copy and paste my chemical equation. All right, and I'm gonna save y'all some writing up here. I'm gonna go through this the long way and then show you there's no need to go through it the long way, and we can kind of shortcut it a little bit. All right, so I'm gonna do the same steps I always do. So I guess when in doubt, fall back on the same strategy we've been using over and over and over again, right? But I'm going to show you why it simplifies a little bit. So first of all, acid-base reaction's the same. My ice table's the same. All right, we said that we had our same initial 87.5 millimoles of our weak acid, and if we're at the equivalence point, how many millimoles of strong base must I have? 87.5. None, none. Our reactants decrease. Our products increase. So we get 87.5 minus X. 87.5 minus X, X, and X. And just as before, since this reaction included that strong base, it must go to completion, meaning all of my limiting reactant is going to be consumed. But in this case, I have the exact same amount of acid as I do strong base. So what's my value of X going to be? 87.5, which means I have no weak acid, no strong base, 87.5 millimoles of conjugate base, and I made 87.5 millimoles of water. All right. But which one of these do I not care about? The water. So then at this point in my solution, I don't have any weak acid. I don't have any strong base. The only thing that I'm left with is a solution of weak base here. All right, so at our equivalence point of a weak acid strong base titration, what we are left with is simply a solution of that weak conjugate base. And since I started out with 87.5 millimoles of my weak acid, and I added exactly 87.5 millimoles of strong base, how much of that weak base do I have? 87.5 millimoles, right? So again, you can do an ice table, all that jazz, or we can just make note that at the equivalence point, the amount of acid initially is going to equal the amount of strong base added, which is also going to equal the millimoles of weak base at equilibrium. All right, so this is going to be an important relationship here that we can use. All right. So that's the good news. We could simplify the how much a reaction has occurred step. We know how much of that weak base is going to be produced. The bad news is we have a solution of weak base, and now we got to calculate its pH. All right, we're going to do that by calculating the pH of a weak base solution. Meaning the first thing that we need is the concentration of that weak base. All right, so my concentration here is going to equal my millimoles of my weak base divided by my milliliters of solution. Everybody take a second. Given what we've solved up until this point, see if you can't tell me what that concentration is. All right, so I got my millimoles. We established that. That was the easy part. What's the volume of this solution going to be? All right, so we got to be careful. We started out with 70 milliliters. That's how much acid we had initially. But then we had to calculate how much base we added in there in order to get to our equivalence point. And that was that calculation we did, at the very beginning, establishing that there were 77.43 mils added to get to this point in our titration. All right, so this was how much base we added in order to get to that equivalence point. So at my equivalence point of a weak acid strong base titration, all I have is a solution of weak base, and I need to calculate that solution of weak base. I get a concentration of 0.59 molar. Okay. All right, and our question is, what is the pH of this weak base solution? So now we got to go back to our strategy for calculating solutions of weak bases. We had our base dissociation reaction. Then we had to do that Kb expression. And then lastly, we had to do an ice table just to fill it all in. All right, now one of the nice things is that at this point we've already accounted for that change in volume. So my ice table I get to keep in units of molarity. I will say it always works. If you really wanted to go to millimoles, you could always do that. You then just have to convert back at the end. It would kind of be a pain, but you could always do that if you really wanted. But noting that we already accounted for the change in volume here, we just need to do our ice table in millimoles. All right, so everybody take a second. We talked about weak bases 2 weeks ago now. All right, so calculate the pH of this weak base solution for me. All right, so we've seen like 2 uses of ice tables, and so I just want to point these out because it's really important to sort of be able to see the difference here and not get confused on how we use each of them. All right, so first of all, we've been using ice tables for 2 reasons. One, to keep track of how much of a chemical reaction has occurred. All right, so given this chemical reaction here, we were figuring out how much of this reaction occurred, but this reaction went all the way to completion. So when we were solving for that value of x, I guess that's always our goal, solve for x in that ice table. But how we were approaching it was very different in this previous way, because we said, all right, this reaction goes all the way to completion, so I'm going to look at what my limiting reactant is. That tells me what my value of x is. In this one here, this is not a reaction that goes all the way to completion. This is an equilibrium problem here. So now what we're going to be doing is using our equilibrium boxes and plugging them back into our equilibrium expression in order to solve for x. Okay? So 2 different uses in which we see our ice table. The difference being, is this reaction in an equilibrium or does it go all the way to completion? All right, so for this one here, I'm going to have to take this value, 0.59 minus x, plug it in for my equilibrium concentration of conjugate base. I'm going to take this x, plug it in up here, and this x, plug it in up here. So this gets me Kb equals x squared over 0.59 minus x. Now I got too many variables. All right, so I got to figure out what Kb is before I can go and solve this equation here. But I'm going to go to my constants page. I'm going to go down to the bottom here, and I'm going to search for acetate for a really long time and conclude that it is nowhere to be found on this table here. So how am I supposed to figure out the Kb of this weak base? What am I going to use? The Ka of its conjugate, because there's that relationship that we're going to take advantage of where Ka times Kb equals Kw, or that magic 10 to the negative 14 number. All right, I don't know acetate's Kb, but I know acetic acid's Ka, so I can rearrange this equation here. 10 to the negative 14 divided by Ka gets me my Kb. All right, so really we're going to set this, we need our Kb. We're going to do 10 to the negative 14 divided by that Ka value that we do know. All right. We could use our real x solution using our fancy calculator. In this case, I'm going to use my small x approximation. Again, that's what I would expect you to be able to be doing on your exam, is using your small x approximation. On your homework, I do make you do real x calculations, but on the exam, you can use your small x approximation. All right, you should be able to tell me whether or not it's okay using that percent ionization. But small x means we're going to ignore the minus x in the denominator. So this becomes 10 to the negative 14 divided by that 1.8 times 10 to the negative 5. That equals x squared over 0.59. Or if I rearrange this here, I get x equals the square root of that Kb, 10 to the negative 14 over Ka, times that concentration of 0.59. And I get a value of x equal to 1.82 times 10 to the negative 10. Seems incredibly small. Okay. Oh my God, that was so much work, so I'm done, right? No. Okay, bummer. So first of all, I just want to note, if your value is a little bit different, I did use my unrounded value instead of 0.59. Use that value for my calculator. But X is our concentration of what? Let's go back to our table. Hydroxide, because we were talking about a weak base. So I can get the POH by doing the negative log of that hydroxide concentration. What went wrong here? Loading. Someone wrong here. What? No. Then this? Yeah. Wonderful, because that was what I thought looked wrong. Oh, I made the exact mistake that I warned y'all not to. Oh man, you know what I didn't do? I didn't put this friggin' thing in parentheses here. Okay, that checks out. $1.82 for sure, but times 10 to the negative, definitely not 10. 10 to the negative 5. There we go. Okay. All right, so then my POH is 4.74, making my pH 14 minus that value, or 9.226. All right. I will say, just FYI, the reason that I was like, oh man, that's definitely wrong, is because when I calculated my pH, it was an acidic pH, and I'm like, hold on, this is a weak base solution. That doesn't check out, right? So again, just like that, like take a step back and double check, like sanity check that your number makes sense, can save you a mistake sometimes. All right? And notice, unfortunately, I told you that the easiest thing I could ask you is the pH of a strong acid, strong base titration at the equivalence point, because it's always 7. The worst thing I could ask you is the pH at the equivalence point of a weak acid, strong base titration, because you got to do all this work to calculate your pH of your weak base solution. And notice that, yes, no, it is not at pH of 7. All right, so we got one more region to go here. Now we're in this region here, which means we have an excess of what? Now that we're past our equivalence point, the base, right? So now I have an excess of my strong base in there, which is why I'm at this really high pH. All right, so let's do a region 4 calculation. I guess let's just make our notes about our equivalence point. We have a solution of weak conjugate base. We have to calculate that weak base concentration. And then we have to do our calculation of a weak base pH. All right, remember, we're going to make our lives easier by noting that we can calculate our weak base concentration, just making note that the millimoles of acid that we had initially are going to equal the amount of base added, the millimoles of base added, but more importantly are going to equal the millimoles of weak base at equilibrium. All right, let's finish off this curve here. Region 4. And we got that excess of that strong base. So now we're going to blow past that 77 mils at the equivalence point, and we're going to add a total of 95 mils of that strong base. Okay, I'm going to be, again, lazy and copy and paste since we're talking about the same acid-base reaction. I could even copy my ice table here for the most part at least. All right, so take a second and fill this table in for this portion of our titration curve. All right, so what's the value of x going to be here? 87.5. All right, so how do we get that here? Importantly, because there is a strong in this reaction, in this case a strong base, this reaction is going to go 100% to completion. All right, so all that strong that will react, that can react, will react, but here I'm limited by the amount of weak base, by the amount of weak acid I have. So all my weak acid is going to be consumed, meaning that x takes on a value of 87.5. So then I got to calculate in my solve row for all the other ones now. I got 19.85 millimoles of my strong base. I have 87.5 millimoles. I'll put my units in here to be good. Of weak base, and 87.5 millimoles of water. All right. Cool. So now I don't have any of that weak acid left over because we're past the equivalence point. I don't care how much water I made because it's neutral. All right, so what we've just demonstrated is that at this point in our titration, we're left with a solution that's a mixture of strong base and weak base. All right, and in your homework, I made you do the long calculations to account for the contribution of that weak one in there. And 99.9% of the time, you would have seen that it was a gigantic waste of time, right? Because when in this mixture of strong base and weak base, the thing that's going to contribute to the hydroxide concentration the most, by far, is going to be that strong base. So we get to ignore this one as well, but for a different reason. And it sounds kind of mean, but we say that in a mixture of strong and weak, we get to ignore the weak. All right, so what we're left with effectively at this point in my titration curve is just a mixture of that strong acid, a strong base solution. Just that solution of that strong hydroxide base. All right, so we're going to calculate the pH of our solution. Okay, the only thing is that in order to do so, we need our concentration. So step one is what is the concentration of hydroxide? And from there, you can calculate the pH of that solution. All right, so given what we discussed, everybody take a second, calculate hydroxide concentration, calculate the pH of this solution. All right, so I have my hydroxide ion concentration, but in order to get my pH, I got to use that auto-ionization relationship. Previously, I used that log form, pH plus POH equals 14. I just want to convince you that it's the exact same if I used my original form of my auto-ionization equation. All right, either one of these will work. If I took that 10 to the negative 14 and divided it by my hydroxide ion concentration, I would get a hydronium concentration of 8.31 times 10 to the negative 14. And if I did my pH equals negative log of hydronium, I would get a pH of 13.08. Does this check out for a solution of strong base here?
Yeah.
That's super high pH, right? So this isn't a weak base, this is a strong base here. All right, cool. So last region we have here, now we have excess of strong base. So at the end we're gonna get a mixture of weak acid, of weak base and strong base, but we're gonna ignore the weak. All right, let me make some room. So we still have to calculate how much of our reaction has occurred. All right, but what we're going to find is that we have an excess of strong base. So when we go to calculate our pH, we're going to use that ignore the weak approximation. All right. So again, our goal here is for every point along this titration curve, we know how to calculate the pH of this solution here. And we have these four regions. Before we start, so just a solution of weak acid, we have our equivalence point where our moles of our acid initially equal the moles of base added and also equal the moles of our weak base at equilibrium. Between those two regions, we have this buffer region here. And then after that, we have this excess of strong base. All right, so our strategy is a little bit different depending on what region we're in. But nonetheless, we can calculate our pH at any point along this curve. One other thing I want to point out here is like I could look at this curve and I know it's a weak acid strong base titration as opposed to a strong acid strong base titration. So let me just point out these subtle differences. Going back to this curve here, number one, the first thing about this is that my equivalence point is exactly at pH 7. Right? That's only true for your strong acid, strong base titrations. The other thing is the shape at the very beginning here. Notice how this one just kind of starts to linearly accelerate up, whereas if I go over here, I'm going to get rid of my color here for a second just to prove a point. It doesn't go up steadily. There's like this huge jump that happens in my pH, and then it starts to level out here. All right, so why is that? Why do I have a big jump at the beginning and then we get this part here? All right, so remember what it means to be a buffer. If this is my buffer region, that's because I'm adding base, but my pH is not changing very much, right? My buffer region buffers, resist pH changes. So then why would it be really bad at resisting pH changes over here and over here? Well, remember we have that effective buffer region. A buffer is only good within plus or minus 1 units of its pKa. So these regions out here are now outside of my effective buffer region, which is why it's no longer able to resist changes in pH. All right, we are now here outside that effective buffer region. All right, so again, we can just look at this curve, and based on that shape, based on that strong acceleration at the beginning here, we know that this must be a weak acid, strong base titration. Cool. All right. Break. Yes, it is.
Okay, so this video needs to be
No, there's not going to be a review, unfortunately.
Okay.
Yep. I can post an old video.
Oh no.
No, we don't.
Yeah, well,
Ready to go right now.
I will post an old video, but no, I mean, it just doesn't make sense because, well, we have new stuff to learn next class period. And on Tuesday,